Hello everyone. Welcome to part 4 in our series on solving differential equations using Laplace transforms. Today we're going to be looking at a couple more examples of differential equations that we can solve so that we can see what kinds of issues you typically encounter when using the method of Laplace transforms. I've already gone ahead and written down some of the results that we have from our previous videos in the series. Here's the Laplace transform of a derivative. I'm using the notation of capital Y for the Laplace transform of lowercase y. Here's our table that we actually filled in by taking the Laplace transform of these various functions. I've also added a couple more rows here. These are called the hyperbolic functions. This is called the hyperbolic cosine, or cosh. This is called the hyperbolic sine, or a cinch. Cosh of AT is defined as in green right here, and cinch of AT is defined in green here. And you can see why we make a connection, right? Look at the transform of cosh. It looks very similar to the transform of cosine. And same thing for sine and cinch. In total, this table is a really good library of transforms of functions that we're going to need. Now, we also need one more result. We need the Laplace transform of the derivative of y. Well, I can use my equation in red. I can use this equation and basically replace y with y prime. Why not? If this equation applies to y, then it's also going to apply to y prime. Okay, how do I do that? Well, the transform of y becomes the transform of y prime. Instead of y of 0, I have y prime of 0. Okay, well, I can use the formula right here to replace the Laplace transform of y prime. In parentheses, I'm going to have sy minus y of 0. And I still have minus y prime of 0. That wasn't so bad. That equals s squared of y minus sy of 0 minus y prime of 0. There it is. We have a nice new shiny formula for the Laplace transform of the second derivative. And you could continue this process to find the Laplace transform of the third derivative, fourth derivative, etc., etc. All right, let's go on to solving differential equations. Okay, so there's our two results in red for the Laplace transforms of derivatives. Here's the equation I want to solve today. Okay, it's a second order differential equation with constant coefficients. And if you've solved these types of equations before, great. Today we're going to use Laplace transforms to basically get the same result. Okay. There's the equation, and I have two initial conditions. So I'm going to take the Laplace transform of both sides using my red equations here to substitute. All right, here we go. Okay, let's take the Laplace transform of y double prime. Well, using my red formula, I get s squared y minus sy of 0 minus y prime of 0. Now I'm going to subtract the Laplace transform of y prime. For that, we need this formula. So that's just minus sy minus y of 0. I need to take the Laplace transform of this part. Well, that's just minus 2y. And that whole thing, that's the left-hand side, that's equal to 0, because that's the Laplace transform of the right-hand side. Okay. Now, notice that anywhere I see a y of 0, I can cross that out because that's actually 0. So I'm going to get rid of that. I'm going to get rid of this. Okay. So let's collect all the terms where I have a capital Y, s squared y minus sy minus 2y. Okay, what's left? I have this y prime of 0 here. Well, that's just 3. And there's actually nothing else. So I'm just going to move that to the other side. 3. Okay, let's solve that for y, which is capital Y. Remember, that's the transform of little y, which is what we're trying to find. So I get 3 all over, big fraction here. If you factor out the y out of this, you get s squared minus s minus 2. You can factor that polynomial into s minus 2, s plus 1. There we go. Okay, we're getting somewhere now. Okay, we're going to need the method of partial fraction decomposition. That's kind of like going backwards. Normally we combine fractions with common denominators. Partial fraction decomposition is the opposite of that. We split apart one big fraction into two separate fractions. Okay. The way we do this is that we multiply both sides of this big equation by this denominator, and I get 3 equals a times s plus 1 plus b times s minus 2. Okay, I'm going to move that over here. Okay. Now, this must work for any value of s. So, for example, if I plug in s equals 2, then what does the equation become? 3 equals, this term disappears, this term becomes 3a. So a must be equal to 1. That was nice. I kind of plugged in 2 because I knew this term was going to disappear. What if I plug in minus 1? Well, now I get 3 equals, now this term disappears. This term gives me minus 3. So I get b is minus 1. Okay, that wasn't so bad. So we get y equals 1 over s minus 2 minus 1 over s plus 1. Okay, this is the transform of our solution, little y. Now here's where we use our table. Going back to our table, I'm going to look at these functions and see if I see any, and then go backwards to the function that I must have started with. And actually, we're only going to need this one right here. The transform of e to the at is 1 over s minus a. So let's look at what we have. Here is 1 over s minus 2. Well, that should remind you that this was the transform of e to the 2t. And here this looks a little big. I want to emphasize that this is our solution function. The transform of this is this. Similarly, the transform, or the reverse transform of this, must be e to the minus t. If I take the transform of this, I get this. So that's it. We've got our answer. This is the answer to the differential equation. And you notice I didn't really need to plug in the initial conditions. That's because we already built those in. If I go back up here, I built those in when I substituted y of 0 and y prime of 0. So this is our answer. We could have gotten that using traditional techniques, but we can also get it using Laplace transforms. Okay, let's do one more differential equation. Maybe a little tougher one this time. Okay. Y double prime minus y is equal to cinch of 2t, the hyperbolic sine of 2t. What's great is that even though this is more complicated, we're going to use the same method to solve this differential equation. Here we go. Take the transform of both sides. I'm going to get s squared y minus sy of 0 minus y prime of 0. That was the Laplace transform of this, minus capital Y equals, now we have to take the Laplace transform of this. For that, we're just going to use the table. Here, a is going to be 2, so I get 2 over s squared minus 4. Okay, I didn't even give you any initial conditions here. I better give you that. So y of 0 is 1, and y prime of 0 is 5/3. Oh, that's not very nice. Well, let's see what we get. Okay, as always, I collect my terms that have big Y. Okay, it looks like I only have 2 terms with big Y. So I get Y times s squared minus 1. Okay, minus s times y of 0. I'm just going to put that on the other side. Put everything on the other side. So I get s of y 0. That's just s. Then I get plus 5/3. That's y prime of 0. And then I get whatever is still there on the right-hand side. 2 over s squared minus 4. I have to admit, this doesn't look particularly nice. But I've got my equation for big Y, s over s squared minus 1, plus 5/3 times 1 over s squared minus 1, plus 2, and this is a big fraction, 2 all over s squared minus 1, s squared minus 4. Okay. Well, parts of this equation look pretty good. This is actually the Laplace transform of cosh, hyperbolic cosine, of t. This is the Laplace transform of 1, right? It's sinh of 1t, or sinh of t. That's this guy right here. So really, we have to work on this one. And as usual, we're going to try to break this up into separate fractions using partial fractions. Okay. So we want to know 2 over s squared minus 1, s squared minus 4. That's going to be we're going to have an s squared minus 1 in one fraction and s squared minus 4 in another fraction. Okay, now you can do this using partial fraction decomposition as usual, and you would put as plus b here, cs plus d here, and you would go through the method to solve for a, b, c, and d. I'm going to take a little bit of a shortcut. I see a number over here. That means when I add these fractions or subtract these fractions, I need to have s squared completely cancel. So I'm going to need a minus sign. Because remember, when we combine these with a common denominator, I'm going to have s squared minus 4 up here and s squared minus 1 here. If I have a minus sign, the s squareds cancel. Now, if I just have a 1 here and a 1 here, what do I get when I actually subtract these fractions? I'm going to get a minus 4 plus 1, right? Minus minus 1. So minus 4 plus 1, that would give me minus 3. But I want 2. So I just multiply by minus 2/3. This minus 3 cancels the minus 3 that I get up here, or it cancels the 3 I get up here, and that's going to give me a 2. That's pretty cool, right? If that was too fast or tricky, you can always do this with as plus b and cs plus d. It's just going to take you a little longer. Okay, so that whole mess, this whole mess should go right here. But this is great because I recognize these two things. These look like hyperbolic sine, just with different numbers for a. Okay. Let's write down our little y. Little y of t equals. Okay, what function has a transform that looks like this? Well, that's just hyperbolic cosine cosh of t. How about this function? That's just the transform of hyperbolic sine with a 5/3 in front. Okay, now remember we're replacing this fraction with these two fractions. Okay, what is this the transform of? This is the transform of hyperbolic sine of t. That was nice and easy. Okay, this one's a little tougher. This looks like the transform of the hyperbolic sine of 2t, but that would mean that we need a t in front. Sorry, we need a 2 on the top, but we only have a 1 on the top. So I'm going to make it a 1 by multiplying by 1/2. And these are little tricks that you're going to use over and over again. Let's see if that works, right? The hyperbolic sine of 2t, when I take the transform of it, I get 2 over s squared minus 4. So when I multiply by 1/2, that gives me 1 over s squared minus 4. Okay, we're basically done. Write it all out. Y of t equals cosh of t plus 5/3 cinch minus 2/3 cinch. That's just cinch. And then finally, minus 2/3 times minus 1/2, that's plus 1/3 cinch of 2t. That is the solution of our differential equation. We've already incorporated the initial conditions from up here, right? Y is 0, y prime is 0. I already put those numbers in, so we're done. This is the actual unique answer to the differential equation. I hope you enjoyed this video, and I'll see you next time.